Every continuous linear functional in a Hilbert space can be represented by a single vector. This is the Riesz Representation Theorem. A Hilbert space is defined by its complete inner product structure. It's an arena where we have rigorous definitions for lengths, angles, and limits, allowing us to treat infinite dimensional spaces with the same precision as a 2D plane. Inside this space, we encounter linear functionals, operators that map an input vector to a single scalar output, like a real or complex number. These functionals form the dual space. You can think of them as these abstract black boxes. You feed them an arrow from our space, and they output a number. In general Banach spaces, these dual functionals are entirely distinct algebraic rules. But in a Hilbert space, the geometry allows us to collapse this abstraction. We can represent any continuous functional as a physical arrow living within the space itself. Contrast this with general normed spaces, where functionals remain mathematically separate from the vectors they act upon. In LP spaces, for instance, the dual is the entirely different LQ space. This creates a construction problem. How do we find a single vector that perfectly mimics the behavior of a given abstract functional across an infinite number of possible inputs? The formalization of this connection was a major milestone in the early 20th century, led by mathematicians like Frigyes Riesz. The solution relies on a direct geometric mechanism, the existence of orthogonal projections. Finding this hidden mirroring vector requires us to look past the algebraic rule and analyze the geometric shape of the functional's kernel. The Riesz Representation Theorem states that for every bounded linear functional f on a Hilbert space, there is a unique vector z such that f of x equals the inner product of x and z. Beyond the representation itself, the theorem guarantees that this vector z is unique and that the norm of the functional perfectly equals the norm of the vector. To find this vector, we first need to identify where the functional is inactive. We start with the null space, the set of all vectors that the functional maps to exactly 0. Geometrically, this null space forms a hyperplane passing through the origin. Because the functional is continuous, this plane is a closed subspace. This provides the stable geometric foundation required to build our representative vector. However, if the functional isn't 0, there must be vectors that sit entirely outside this null space plane. This allows us to define the orthogonal complement. Since we are in a Hilbert space, we can draw a line that is perfectly perpendicular to the entire null space plane. This orthogonal complement is exactly one-dimensional. It's the only direction where the functional can see change. We begin by picking any non-zero vector on this perpendicular line to serve as a baseline. We'll call it z0. To finalize the vector z, we scale z0 by dividing the conjugate of the functional's output by the squared norm of z0. This specific scaling ensures that the inner product with z will yield the exact same value as the functional for any input x. The existence of the orthogonal complement provides the physical engine that guarantees our representative vector exists. There is a common misconception that the functional and the representing vector are the same object. They are different. The functional is the abstract rule, while the vector is the geometric embodiment of that rule within the space. This representation also relies entirely on the functional being bounded. If it's unbounded, the null space is no longer a closed plane, and our perpendicular direction can vanish entirely. We can see this in action by testing the theorem in tangible spaces. Consider Kreyszig's example of the standard 3D Euclidean space, R3. In this environment, every linear functional is just a standard dot product with some fixed vector, A. The same logic holds as we move to the infinite dimensions of the sequence space, L2. Here, the functional is represented by a cascading sum of the input sequence paired with a fixed representative sequence. Whether the space has 3 dimensions or infinite sequences, the inner product maps the abstract rule back to a geometric vector. This leads to a bigger question. Can we scale this logic beyond single variable functionals? This brings us to sesquilinear forms, operations that take 2 vector inputs to produce a single scalar. If we hold the input y fixed, the form behaves exactly like a standard linear functional acting on x. Applying the Riesz theorem to this functional produces a unique representative vector for that specific y. If we repeat this for every y in the space, we define a continuous mapping, a bounded linear operator. This geometric logic allows us to move from representing single functionals to defining the behavior of entire operators. Let's look at a bounded linear operator t acting within our inner product. The expression of t acting on x, inner producted with y, creates a bounded sesquilinear form. Since the inner product of tx and y is a functional on x, Riesz's theorem guarantees there is a unique vector representing it. By mapping every y to its corresponding representative, we construct the Hilbert adjoint operator t star. While the adjoint mirrors the matrix transpose familiar from linear algebra, in infinite dimensions it emerges as a necessary geometric consequence of the Riesz Representation Theorem. This framework provides the specific mathematical language needed to model quantum mechanics. Quantum mechanics uses self-adjoint operators, where t equals its own adjoint, to represent fundamental physical observables like energy and momentum. This structure also allows us to solve complex partial differential equations and perform Fourier analysis. We have moved from an abstract rule to a specific perpendicular vector, and finally to the construction of a unique operator pairing. If you want to understand how these operators map the rest of functional analysis, hit subscribe, check the links in the description for recommended texts, and join us next time as we dive into operator theory.